So, substitution reaction. In organic chemistry, we have so many reaction types, and this specific reaction characterized by replacement of an atom or a group of atoms from one compound to another compound is referred to as substitution reaction. And in this experiment, we will be looking at one of the major kind of substitution reactions. I mean, we have nucleophilic substitution reaction and electrophilic substitution reaction, but we will be focusing on the nucleophilic substitution reaction in this experiment. And this is important reaction that so many compounds, so many functional group exchanges are formed as a result of this reaction. The general overview of this reaction is that we have a substrate, mostly alkyl halide, and a nucleophile and an electron-rich species, which could be negatively charged, like the carbanion or the amide or the alkoxide, or it can also be neutral, like water, alcohol, and ammonia, or any amine compounds. And then when the nucleophile reacts with the substrate, it gives us the product. However, the product is formed when the nucleophile replaces the leaving group, and then we shall see the leaving group at the end of the reaction. So any nucleophilic substitution reaction must have this feature if we are going to call it substitution reaction. Nucleophilic reactions have two classes, mainly two classes. The S stands for substitution, N stands for nucleophilic, because there is participation of nucleophile in all substitution reactions, whereas the numerical exponents 2 and 1 refers to unimolecular and biomolecular. A biomolecular substitution reaction means simply the reaction rate is determined by concentration of two of the reactants, whereas if it is unimolecular, the reaction rate is determined by concentration of one of the reactants. There are three major factors that affect SN2 and SN1 reactions. The first factor out of them is the nature of the substrate. Remember, I told you that the substitution reaction is, the overview of substitution reaction is that there is the substrate and a nucleophile as reactants. So that substrate is Rx most of the time, alkyl halide, but X might not necessarily be halide. So if we have so many substances around the carbon atom, which is a highly substituted carbon atom, then the degree of that carbon atom increases to secondary and tertiary, and it will favor to undergo SN1 reaction. However, if a given carbon atom is substituted by less atoms, less sized atoms, like hydrogens, for instance, in the case of methyl halide, or by one or two carbons in the case of ethane and isopropane, ethynyl chloride or isopropenyl chloride, where two carbons surround that given atom. Those kinds of structures are better to react by the SN2 reaction mechanism. So for SN1 reaction, for SN1 reaction, it will be most reactive if the substrate is tertiary, and it will reduce if it is secondary and all the way to primary. Whereas for SN2 reaction, this order will be the reverse. The second factor that affects these reactions oppositely, of course, is the nature of the nucleophile. SN2 reaction favors negatively charged nucleophiles because the nucleophile is supposed to start the reaction in SN2 reaction, and it has to be very reactive. A reactive nucleophile is if it has negative charge in it, which means it's unstable and it urges to give this negatively charged, these unpaired electrons, and as a result it happens to be more reactive. Whereas in SN1 reaction, the first reaction does not involve the nucleophile, and there is no any role of the nucleophile, and neutral nucleophiles are favored. In fact, because nucleophile in SN1 reaction is favored to remove the proton in the middle of the process than to actually push the leaving group. Third factor is nature of solvent. Solvents which has hydrogen bonds in their chemical structure are called polar protic solvents, and solvents which lack hydrogen bonding in their chemical structure are called aprotic. Examples: you can have dimethyl sulfoxide, and you can have dimethyl formamide and acetone. All these are polar aprotic solvents. Whereas for polar protic solvents, water itself, alcohol itself is an example, or acid, for instance, are also an example of polar protic solvents. So these three are major factors that determine SN1 and SN2 reaction. However, these reactions are also affected by leaving groups. Consider the halide leaving groups. For instance, a leaving group, a halide leaving group, which is less electronegative and bigger in size, is better leaving group compared to a halogen with less leaving group with a smaller size and high electronegativity. That's why if you see the order of halogens under the SN1 column, you will not see fluorine, because it's hard for fluorine to detach it from hydrogen, and fluorine is a bad leaving group. So anyway, both of them prefer strong leaving, good leaving groups. When the reaction happens, the SN1 reaction results in racemic mixture. If the original compound has had S configuration, and the product will have S or R configuration. Conversely, in SN2 reaction, if the original compound had S configuration, the nucleophile will attack it from the opposite direction, and the product will have R configuration. If it was R, the product will be S. If it was S, the product will be R. SN2 reaction is a single-step reaction where there is a very shortly leaving transition state, but no carbocation. So bond formation and bond breakage occurs at the same time, whereas SN1 it goes through 3 steps. The first step is carbocation generation, second step is nucleophilic attack, and the third step is deprotonation. So let's see an example with SN1 reaction in tertbutanol. So this tertbutanol reacts with hydrochloric acid, where this hydrogen chloride is the source of the nucleophile to give us tertbutyl chloride and water. Because if you see the tertbutyl chloride, the carbon is surrounded by 3 carbon atoms, so that it's tertiary and it favors the SN1 reaction. So, however, here you see we do not start with deprotonation or with the carbocation formation, because the OH group is a bad leaving group and we have to protonate it first. But in most of the SN1 reactions, we start from carbocation formation and we go to nucleophilic attack, and then we go to deprotonation because we have to use a neutral nucleophile. But anyway, the first we have to deprotonate the OH group, and then this reaction is fast, giving us oxonium ion. So you see oxygen is electronegative atom, and in addition to that, it has a plus sign on it, means it's really starving for electrons. So what it needs is, it just needs a pair of electrons to isolate itself from the structure. So the bonding electrons will be given to oxygen, and you will have the water as a byproduct and a carbocation formed as a result. And finally, the nucleophile, the chloride ion, comes and hit the carbocation, and we will have the product. So some students think that because we are shifting electrons, that substitution reactions are actually oxidation reduction reactions. However, the answer is not. They're not. Why? Because we're not transferring electrons, we're simply transferring a proton. If you look at the first mechanism, for instance, the pair of electrons from oxygen are not transferred to hydrogen. Simply, we are transferring proton, or they are simply shared between hydrogen, not transferred. So in today's experiment, we will try to convert tertbutyl alcohol to tertbutyl chloride through SN1 reaction mechanisms. The chemicals we need are hydrochloric acid, tertbutyl alcohol as a substrate, and sodium bicarbonate to neutralize the acidity, and we need also anhydrous calcium dichloride just to dehydrate our final product. Major equipments we will be using today are pipettes, both plastic and glass pipettes, as well as test tube. The plastic pipettes are disposable, and we use them when we want during the rewashing step, whereas of course the glass pipettes are also disposable, but the bulb can be reused if it is washed appropriately. In this experiment, we will be using alcohol and acid. Both of them actually should be handled with great care. However, acid, it's hydrochloric acid, and you may know that this is one of the strong acids, and let alone it comes in contact with our skin, the vapor that comes from the containers of this acid itself can cause severe respiratory irritation and damage. So the best way to do to work this experiment so that you can minimize inhalation is to entirely do the experiment in the fume hood. And as usual, you're expected to wear safety gloves and safety goggles. So the actual procedure for the experiment starts by adding 50 milliliters of concentrated hydrochloric acid, and then you add 3.9 gram or about 5 milliliters of tertibutyl alcohol. If you have, you have to prepare this solution in that amount. At the beginning, these mixtures will form a layer, but that layer is not clear, which means it needs further mixing. To do the mixing, you have to use the plastic pasteur pipette, and the mixing is specifically called squirting technique. And the right way to do is you insert the plastic pipette to the test tube containing the mixtures, and you have to lower the mouth of the pipette to the middle of the liquid as much as possible, and then you have to draw the liquid in and draw the liquid out, and you have to do this for several times for about 15 to 20 minutes so that you can effectively mix these mixtures. We will be doing this several times during the experiment, and please remember not to reuse the plastic pasteur pipette. You use it here in the further experiments. Then you take that final sample where you see a clear layer, where the top layer is the organic layer and the bottom layer is the aqueous layer, and you remove the aqueous layer using a pasteur glass pipette. And this pasteur glass pipette have very narrow and tall mouths. It will allow you to carefully remove this bottom layer, the aqueous solution, and it can also the bulb is so soft that it makes it easy to control the flow of this liquid while you are sucking, while you are drawing the liquid towards it. And then take this sample, again add water, just this part is just a washing process, and then do the squirting technique, just wash using a plastic pipette, pasteur pipette, by drawing in and out the water, and finally remove the lower layer using a glass pipette, and keep the sample for the next procedure. Then you take that sample and you add 5% of sodium bicarbonate prepared with distilled water. We do this simply to neutralize the acidity. And again, you do the washing for several times for about 15 to 20 minutes again. Then you remove the sodium bicarbonate layer, which is the bottom layer, and then you keep this final sample for the next procedure. So in this procedure again, it's washing with water. You add water, you make the washing, and then you remove the water molecule so that the water liquid, so that so that it will assure you that there will not be any traces of sodium bicarbonate left. And finally, that's the end of the washing and rewashing process. You have to then transfer the organic layer into a dry clean test tube having about 1 gram of anhydrous calcium dichloride, and take this sample again and transfer it to a small round bottom flask, about 25 milliliter round bottom flask, and you undergo this simple pass distillation. So this is simply the representation of the simple distillation, but of course below the round bottom flask you have to assume we have heat source, and then we have the sample there in our round bottom flask. We start the heating and the mixture will start boiling, and you will see droplets in the arm of this edge-shaped adapter. Specifically, try to look for distillates in about 49 to 50 degrees Celsius temperature. That's why you need the thermometer when you do this experiment. Sorry. Here, when you assemble this apparatus, please remember to grease the joints so that you will not have any blockage as a result of that. However, sometimes the distillates might not be formed, and what you should do here is you can bring a clean dry test tube and add an ice or very cold water into it and place in the mouth of this adapter, and that helps a condensation to occur, and then you can have the distillate in the end. However, there is a chance that if your test tube is not clean and dry, the droplets might not be from the reaction but from the water itself, and you need to make sure that that does not happen in the experiment. And finally, you got to calculate the yield of the experiment, and we assume you will find about 2 grams of tetrabutyl chloride in the end. And this might not also happen, so you can calculate your yield based on what you get from your experiment. And the way to do that is you have to calculate the theoretical yield because you have the experimental yield. So in this experiment, in the reaction, you saw that 1 mole of tetrabutyl alcohol has reacted with 1 mole of hydrochloric acid to give us 1 mole of tetrabutyl chloride. So this will help you to calculate the theoretical yield, and to do that, because we were using solutions, you can convert the solutions into moles simply by applying the density formula, density mass by volume. From that you can find the mass, what mass is 5 milliliter of tertibutanol, and when you divide that mass by the molecular mass of the tertibutyl alcohol, you will find the moles of the tertibutyl alcohol participated in the reaction. You can do the same for hydrochloric acid, and you apply that balanced reaction to calculate the theoretical yield. The theoretical yield. And finally, percentage yield is calculated as actual yield divided by experimental yield. And if your product was 2 grams, which means you'll have 43% yield, whereas if it is below that, then you guys can calculate that and put it in your lab report. Well, more or less this is what I have for this experiment. If you guys need any clarification in any of the slides, leave me a comment in the YouTube channel, and thank you for your time.